Polarization of electromagnetic wave is the study of the electric field oscillation geometry. It controls and affects the behavior of electromagnetic waves in many situations, especially in boundaries. In this video we will discuss different types of polarization and the origin in each type. Electromagnetic waves composed of a wave of electric field and a wave of magnetic field. The two fields oscillate perpendicular to each other. Also, they oscillate perpendicular to the direction of propagation. For the study of polarization of electromagnetic waves, we will consider and study electric field only. Here, the electric field propagates in z direction, but the electric field vector oscillates in x direction. The polarization of electromagnetic wave is the study of how the electric field is oscillating. Or in another way, what the electric field vector draws in a plane perpendicular to the direction of propagation. For this case, electric field draws a line on this plane, so this type of polarization called linear polarization. This line is a vertical line. So, it is called vertical polarization. Because there is vertical polarization, there must be horizontal polarization. This type occurs where electric field oscillates in the horizontal direction. But what happens when there are horizontal and vertical polarized waves at the same location? Let we consider two electromagnetic waves at the same location. As we say, we draw electric field only. The first one in pink has vertical polarization. The second one in blue has horizontal polarization. We took a screenshot at a given time to see the phase shift between them. The first one has no phase shift from cosine reference wave. Also, the second has no phase shift. So, the two waves are in phase. Now, we add every two vectors at the same location. So, the second wave vectors will start from the end of the first wave vectors. The vertical polarized wave represents the x component. So, in the origin, the x component of the time-varying electric field equals cosine omega t. And the y component is also cosine omega t. Then we will move the time forward. The resultant wave of these two waves is the green wave. The resultant angle is tan inverse the y component over x component, which is 45 degrees. So, the angle not changing. Then, the electric field oscillates in a line. So, it is linear polarization. The line is oblique between vertical axis and horizontal axis. So, it is called oblique polarization. Now, let we shift the horizontal wave -90 degrees. So, in the origin, the x component of the time-varying electric field remains cosine omega t. And the y component turns into sine omega t. Then we will move the time forward. The resultant wave of these two waves is the green wave. The resultant amplitude equals 1 because the trigonometric identity cosine omega t squared plus sine omega t squared equals to 1. The resultant angle is tan inverse the y component over x component, which is omega t, which is continuously increasing with time. So, it rotates counterclockwise. The resultant amplitude is constant and rotates counterclockwise. It draws a circle in a plane perpendicular to the direction of propagation. This polarization is called counterclockwise circular polarization. Now, let we shift the horizontal wave positive 90 degrees. So, in the origin the x component of the time-varying electric field remains cosine omega t. And the y component turns into negative sine omega t. The resultant amplitude equals 1. The resultant angle is tan inverse the y component over x component, which is negative omega t, which is continuously decreasing with time. So, it rotates clockwise. It draws a circle in a plane perpendicular to the direction of propagation. This polarization is called clockwise circular polarization. If the amplitude of one of the electric fields increases, then the circle will bulge and turns into ellipse. So, if the two waves shifted by 90 degrees and the two amplitude is different, the polarization becomes elliptical polarization. Elliptical polarization also may be clockwise or counterclockwise. There is another way to produce elliptical polarization. It is done by changing the phase shift between the two waves by a value not 90 degrees or its multiples. For example, let's consider two electric field with the same amplitude and has phase shift 45 degrees. It produces clockwise elliptical polarization. Also, it may be clockwise or counterclockwise, depending on the sign of the phase shift. At the end, let us summarize our investigations. If there are two linearly polarized electric field waves at the same location, and they are perpendicular to each other, the phase shift between the two waves has three cases. First, it may be 0 or 180 degrees. Then the resultant polarization is linear polarization. Second, it may be 90 or 270 degrees. Then the resultant polarization may be circular or elliptical depending on the amplitudes. If the amplitudes are equal, then it is circular polarization. If the amplitudes not equal, then it is elliptical polarization. Finally, if the phase shift is not 0, 90, 180 or 270 degrees, then it is elliptical polarization.